morning, everyone. I'm Noor, and I'm a PhD student currently doing my PhD with the Tactile Robotics group at the BRL. And I'm going to present my work on sensing ultrasonic mid-air haptics with a biomimetic tactile fingertip. So mid-air haptics is a technology that creates the sensation of touch in the air. And my work focuses on developing an autonomous method for sensing mid-air haptics with a tactile fingertip, which is inspired by the human sense of touch. So the purpose of that is to develop a tool for testing the performance of mid-air haptic devices, and also to understand the transduction of mid-air haptics by the human sense of touch. So the mid-air haptics technology that I use is developed by Ultrasonic, and they use an array of ultrasonic transducers that you can see here, which emit ultrasonic waves in space, and they are concentrated at a single point to create a focal point. And at that focal point, there is generated an acoustic radiation force, which is at the order of millinewtons, which deflects the skin and then evokes a tactile sensation. So then you can feel something as if there's something in the air, but it's just generated by ultrasonic waves. And this technology is referred to as ultrasonic mid-air haptics. And so you can see here that by using a number of focal points and by modulating them at certain paths, so moving them along a certain path, or changing their frequencies, you can generate different feelings. And so what I'm doing is developing a tool to test mid-air haptics. So current methods that exist for testing mid-air haptics tend to have a big trade-off between resolution and time. So for example, you can see on the left is an oil bath, which so you put the ultrasonic array on top of the oil bath to emit the sensations on the surface of the oil, and then you can see the shapes that are generated quite fast. But that is more of a qualitative method rather than a quantitative method. And then you have methods such as laser Doppler vibrometry, which are much more detailed, and you get really data-rich results. However, it uses really costly equipment, and it takes quite a lot of time. And so my work develops a method to use a tactile sensor to test mid-air haptics, which will combine both time efficiency as well as giving us a high resolution of the data. And it is also a biomimetic approach, which means that it's inspired by biology. And so the sensor that I'm using is the Tactile, which is where the biomimetics comes in. And the sensor is inspired by the layered structure of skin, specifically the human fingertip, and it has a rubber-like outer dermis with a gel inner dermis, and it has these pin markers, which are counterparts to mechanoreceptors in human skin. This sensor is modular, and it is 3D printed, and so it has been integrated on many different devices, such as robotic hands. So in my case, I'm using this version of the Tactile, which is a flat one, and it has 127 inner pins, as you can see. And what I've done is I've mounted it on a robotic arm, the ABB arm, to test what the ultrasonic array is emitting. And so here you can see the process of my sensing method. And so we get an image from the Tactile because it's an optical sensor, and then I find the positions of all the pins, and then I apply Aware-ness tessellation, which is the key point in this analysis method. And so the Aware-ness tessellation, what that gives us is a third dimension of the data, which allows us to see the deflection of the surface of the skin. So you can see where the color is yellow, that tells us that there is a stimulus there, or it's feeling something. And so by doing that over a grid, in which the robot moves the sensor incrementally, we can collect many data points over the ultrasonic surface, and then we can generate an image of what the stimulus looks like. So here we can see that there is a focal point that is generated by the ultrasonic waves. And I've also applied this to sense multiple different shapes. And so with the ultrasonic arrays, there are two main methods to generate shapes. One is called amplitude modulation, and the second is spatiotemporal modulation. So with amplitude modulation, you generate a number of focal points in the path of the object that you are trying to create, and you modulate their intensity over time. And so you can see that the Tactile and the method that I've developed is able to sense this, and is able to distinguish between the line stimulus and the circle stimulus. And then with spatiotemporal modulation, you generate one focal point, and you move that over the path of the object, but you keep its intensity constant. And again, you can see that we are able to sense that, and we are able to sense the difference between amplitude modulation and spatiotemporal modulation. And next, what I've done is visualize a focal point in 3D. So when the ultrasonic array is generating a focal point, it is generating it at a specific height. However, due to the nature of the acoustic waves and how they interact, there is a radiation force in three dimensions. So what we need to do is make sure that those other forces aren't interfering with our perception of what the stimulus looks like. Because when a person interacts with the mid-air haptics, they move their hand in 3 dimensions to see what they can feel. And so I repeated the previous process, but over 3 dimensions. And on the left, you can see a simulation of what the acoustic field looks like. And on the right, you can see what we've sensed with the device. So you can see that we can sense the areas in which the acoustic radiation force is at its highest, which means that in a 2D plane, you can feel it as a point, and then in a 2D plane, in the y-axis, you can feel it as this oblong spherical shape. So this is just something to keep in mind while designing mid-air haptic stimuli to make sure that you're generating the desired shape. And then to take that to a next level, so this is what I'm currently working on, is an algorithm for intelligent haptic exploration. So everything I've done so far is using a robot arm to move the sensor in a grid. But what I'm doing now is to use the robot arm to decide where to move next based on what it's feeling. So the reason for that is, one, to have a more efficient data gathering process. So instead of having to sample data over the entire space, we only need to sample data where there is stimuli. And then the second reason is to make it more similar to how a person interacts with their haptics. Because when we interact with it, we don't put our hand and move it in a grid-like fashion. We kind of see what we can feel, and we move around it as we construct the model of what the shape looks like in our mind. And so that algorithm has 3 main parts. So we have the sensing process, which is mainly what I've shown so far. And then there is the perception and action selection modules, which means that we take the data that we've sensed, we make something out of it, we identify where the stimulus is, and then we select an action to take based on what we felt. And that results in the fingertip being moved by the robot, and then the whole process being repeated again. But that work is currently in progress, so I don't have any results to show you. Hopefully next time I will. And so just as a general summary, we can use the tactile fingertip as a useful tool to sense and visualize mid-air haptics. Yeah.
So is it possible with that device to have like a actively moving focal point?
Yes.
So that like you could do an experiment or something that people are actually capable of like tracking that focal point or something?
Yeah, do you mean moving the focal point based on where your hand is?
No, so if you have like the X, Y, Z coordinates, that the focal point can basically like move around.
Yeah.
And that like your active or the person doing this to be able to like sort of feel around and track where their focal point actually is.
Yeah, so that is how they generate shapes using focal points. Okay. So you can emit one focal point and move it along the path. So everything I've shown is just in 2D, so like the circle and the line where they move it. But they also do 3-dimensional as well. So you can generate, as long as you can generate a path of an object in any 3-dimensional shape, and then you move that focal point really fast along that shape, then you should be able to feel that shape in 3-dimensional. Yeah. Yeah, I'll let you know. Okay. Everyone, my name is Nicola. I'm a second-year PhD student at the University of West of England. My supervisors are Manuel Giuliani and Sevin Limanu. And this is my project title. I'm just going to talk a little bit about my project and what I've done so far. First of all, I want you to look at this picture, and I want you to think about what's going on, maybe like what each person's thinking, how they're feeling, is this overall a positive interaction? So as a human, it's pretty easy to look at that picture and extract what's going on. So for example, we'll look at person 3, you can see that they're probably leading the conversation, sort of gesturing, it looks like they're mid-speech. Person 2 is frowning a little bit, maybe disagreeing with what person 3 is saying. Person 1 looks a little bit nervous, you can see their hands sort of in their position. And aside from that, we can sort of assume that there's more people in that interaction based on where everyone's looking, and that people typically don't, just converse and face forward. A robot looking at this picture, they might come to a bit of a different conclusion. So they might look at person 3 and say, they look a bit angry, they're pointing, maybe directed at someone. Person 2 is frowning, maybe a little bit sad. Person 1 is a bit scared, the eyes are wide, the mouth is in that timid position. And overall, they would assume that this is probably a negative interaction. And that we just step in and sort it out. So this example shows that there's a bit of a gap in the existing tools out there to provide a social robot with the human-like social cognition to interpret these sort of interactions in the same way that we would. So we need to have more developed models of social cognition in the future for this to happen. So these are the aims of my project. So the first one, why can robots understand a social situation in some way human would? So just demonstrate that with that picture there. How can social signals be represented entirely in a robot? And can we use multiple social signals? And can we extract signals instead of just programming them all by hand? Now, all of these aims can sort of be summarized with the idea that perceiving and interacting and interpreting these interactions are quite complicated for social robots. And this project sort of frames that. It's something that we call social situation assessment, or SSA, so don't we say that. So in the context of like an artificial system such as a social robot, we can define SSA as the autonomous perception, interpretation, and evaluation by an artificial system of social interactions and experiences. AKA, the robot is able to look onto a social situation and interpret what's going on using the social signals that's being passed around. So this is how they build sort of body of knowledge of that environment that they're in. So now I'm going to talk about data that I recently collected to investigate the aims I just mentioned. So aim of the data set is to collect some sort of data that simply captures group interactions. So obviously with the current COVID situation going on, being that in person wasn't really possible. So I turned to using an online study to get the data that I needed. And I did that in the form of a little game, which hopefully the video is going to work for. Okay, so it's not the best quality, so I apologize. But just give you an idea of what the participants had to do during the game. So at the start, we told them that they are a detective and they have to solve a murder. So their challenge was to go around the town and speak to all the people, sort of gather clues, and at the end they have to tell us who they thought the murderer was, which we obviously didn't care about, but it was fun to see people's sort of thought process behind that. We did the study through Prolific, and we got roughly 92 participants, I can't remember, who successfully completed the game. We removed any participants who had an FPS that was quite low because that probably meant that the game wasn't that playable. So their interactions would be skewed. And then we also had an attention check, so we got that wrong. We collected their demographic information through Prolific, and at the start of the game, we completed a Big Five demographic questionnaire to get that information. So during the interactions in the game, these are the signals that we collected. So proxemics, how far each of the characters were away from each other, gaze direction, which way each of the players facing, the dialogue, which was pre-programmed, but they had a selection at each of the points in the dialogue. And at each point of the dialogue, they could choose which emotion they express that symptom with. So just as an example of the trajectories that some of the players took around the map. So from the data collection, I've designed a metric to capture the interaction from the game and create a measure of how engaged in the interaction each of the participants were. So we only use the frames before, during, and after interaction, so we don't use any of the sort of parts where they're just walking around and reducing the sort of noise, and it makes processing a lot faster. So we took 10 frames plus or minus at the beginning and the end of interaction. Proximity, so how far are each of the players from each other. We took a field of view for each of the characters, and if any of the characters were in that field of view, perhaps they were looking at each other. And then there's a mutual case of looking at each other. This is how the metric was determined. So the lower the distance between characters, and the closer the gaze direction, and the closer to the center of the field of view that someone was, there's an increased likelihood that there is a metric actually going on, and then they are engaged. So with the metric, we also want to see if there's any relationship between the engagement score and demographic information we collected and their personality information. So this work is still being done. So the next steps for this project, firstly, I want to create a model using engagement metric to automatically recognize this social engagement within groups. And this can then be applied in real life to a social robot. And secondly, I want to possibly expand the game to remove the NPCs and replace them with real people interacting, so make it a multiplayer game. So at the moment it's just one player and then NPCs that are sort of pre-programmed. Also, I want to add some more complex behaviors into the game. So at the moment they can't really do a lot. So maybe give the players some sort of tasks to do, so they can move around a bit more, interact with sort of on their terms. This picture here kind of shows where the development is so far. This iteration of the game is in collaboration with the supervisor Severin and one of his master's students as part of their dissertation project. So that will be in development in the next few months. Yes. Thank you.
Other questions?
So during the game, the NPCs, are they always just stood in place, or is there a bit of a dynamic going on with the NPCs themselves?
Currently, they are still in place. It's a bit complicated to have them moving around, like stay within the groups.
Yeah.
Because we wanted them to be either in pairs or by themselves, and it's just too complicated to have them moving around.
And so, I think you mentioned this, but what was the purpose of the 3 faces in the dialogue options?
Oh, yes, in the video. So it's basically so that they could, so because the dialogue was pre-programmed, so they could say something with either a happy expression, angry, or neutral, and the NPCs would respond in like telling based on how they said that thing with that emotion. So if they said something angrily, the NPCs were likely to respond angrily back. They sort of followed like that. They haven't used the emotions too much. This was something I want to look into, so we collected it, but we haven't really used it in the metric. So it doesn't really factor into say like how engaged you are.
Question, so how does this link back to social robots in the first line where you can detect it from a human face on the situation? How does the game link back to that?
Okay, so the picture at the start was really just to say like there's a big gap between how humans and robots look at situations kind of in like a group setting. Like so at the moment they don't really have they'll look at a couple of signals, but they can't really like put it all together. So that's what the picture is for.
Okay, thank you, Nicola.
schedule that we have. Like I only just remember without you because it's they have times that doesn't suit me.
Hi everybody. My name's Mickey. I'm a third year FASCO PhD student, working on sort of looking at planning for failure, providing guarantees for multi-robot mission completion despite robot failures. I'm supervised by Arthur, and I'm also an industrial student sponsored by Toshiba. So, So multi-robot systems offer loads of advantages over single agent systems. So they can increase efficiency, they can increase the system capabilities, throughput, and many other things. So here we have some examples of multi-robot systems in industry. So we've got the car plants, we've got your sort of logistics, your Ocados and Amazons, and then you've got the new Boston Dynamics thing. They're trying to sort of break into this area. But an often quoted improvement for multi-robot systems is that they increase reliability or resilience, or something along those lines. We call those the 3 R's. Resilience, redundancy, and reliability. But if you actually have a think about it, just having multi-robot system doesn't necessarily mean that you get those 3 R's, especially in the real world where robots tend to fail or tend to do things that they're not meant to do. Cool. So I'm aware that the quality of the presentation is a bit hard, so I'm going to skip through slides with a bit more text, just to sort of get to the meat of things. So the 3 R's themselves: resilience. Resilience essentially just means that a system can withstand a number of failures. Redundancy means that you have multiple things there just in case one thing fails, so another thing can take over. And reliability essentially means that the probability that an item will perform a required function without failure for a stated period of time. So that just gives you some background. All right, I'll add this then. So currently, I'm mostly focusing on multi-UAV systems. So currently, multi-UAV systems, essentially, they're just used for show. But actually, UAVs, as you can imagine, they have there's lots of possibilities of using them. You can use them for inspection and things like that. And I'm looking at how we can bring those practically into the real world, because there are a number of questions to answer, especially from the safety side, and how we can sort of design systems to provide the 3 R's. So my own work then looks at the following. So I particularly focus on reliability and how perhaps UAV failure affects the reliability of mission performance. So we know that in the real world, when you're planning a mission or something, you have to somehow ensure performance with respect to time constraints and external risks. However, a lot of UAVs, especially sort of the ones that are affordable, are sort of they're sort of manufactured. They are prone to failures. So multi-UAV solutions have the sort of ability to provide more flexible, scalable sort of approaches, but also multi-UAV approaches can give the tolerance to individual failures. However, the problem there is sort of more challenging coordination. How do we do this coordination? So let's give an example. So for instance, you've been hired to inspect this railway bridge. You have, say, 2 hours until the next train. So that is your deadline. You have 2 hours to finish this inspection. So a traditional solution would essentially be to split the inspection between multiple drones equally. But the drones don't overlap or anything. It's just you have one drone doing the underside, another drone doing the top, and so on and so forth. This we refer to as the sort of multi-agent coverage path planning solution. Sort of simply split up the environment and let each agent do its own environment in its own way. The downside is what happens when a drone fails. If that drone fails, then another drone has to be reactively rerouted to cover the missing drone's area. And this might cause a delay, so far as in sort of causing you to miss the deadline, which is exactly not what you want. So we're looking at sort of solutions to solve this problem. How can we provide some guarantees that the mission will be completed by the deadline, given that your drones can fail at any time? So let's consider the fact that you can model failure probabilistically. So you can say that my particular drones have a particular failure curve. Then with this failure curve, we can introduce some notion of probability of mission completion. So the drones can fail at any time along with the probability given by the curve. Can we combine those somehow with the planning to produce a path plan which can maximize the probability that the mission will be completed? We call this problem the reliability-aware multi-UAV coverage path planning problem. A mouthful, yes, but it fully describes the problem we're trying to solve. And the problem is, indeed, how do we maximize the probability of mission completion by the given deadline? We call it T-bar here. So this is a bit wordy, but essentially take you through it. So the goal that I'm trying to solve essentially is to find a path plan for each robot which maximizes this idea of probability of completion, such that every part of the environment will be covered by the deadline. So this differs from things like multi-agent coverage path planning without the reliability aware, because in that, we're solely minimizing travel costs. We don't consider things like task revisiting, which introduce some notion of redundancy, which sort of increase the reliability as well. And it's also different from, say, reactive failure strategies where, we plan assuming no failures, but then sort of if one fails, we then have to reactively replan and all those sorts of things. Here, we're just sort of finding the a priori maximum reliability routes, such that if an agent does fail, it's fine. We know that we have guaranteed a certain probability of completion, even if they fail. So I've been working on this problem for the past 2 years, and we've gone through multiple iterations of sort of how to propose the problem and then how to solve the problem. So previous work, we sort of looked at the simple case of sort of synchronous agents moving around a lattice type thing. But my most recent contributions include sort of extending this idea to less constrained scenarios. Particularly, we can solve this problem in continuous time, allowing for more realistic, say, asynchronous moves with agents moving around sort of as they want, and tasks of varying duration as well, to simulate things like travel time, or if a particular, say, inspection area needs a bit more time for a better sort of inspection. And secondly, my second contribution is I've produced a solution, a solving method for this problem, and we've termed this the greedy genetic algorithm. So there's a little bit of idea about the genetic algorithm. Essentially, what we're doing here is we're greedily choosing the best, the path for a single agent that maximizes reliability given previously found paths. So we're iterating through, adding one agent's path at a time, trying to maximize reliability. So each time we're greedily choosing the best. That's the greedy bit. But we'll get away from all the text and we'll show some results. So I'm just saying here that we're evaluating against a bunch of different things. Importantly, we're evaluating against what I've called here, I don't know if you can see it, but partition methods, which represent the multi-agent coverage. Another interesting fact is, I don't know if you see on the left, but essentially this model we've created allows you to plug any sort of failure model in. So here we model agent failure with a bathtub curve, which essentially models the 3 life stages of the product. Sort of if a product has early failure due to mechanical defects or construction defects, it then models the sort of the lifetime failure, sort of constant random failure during its lifetime, and then models its sort of end of life wearing out type things. So with these, we can sort of do an evaluation. So we have 3 scenarios. So we have 2 aeroplane inspection scenarios and one of the BRL, a laboratory tour. And the aeroplane scenarios, we do an inspection with 4 drones, and the lab tour we do with 3 drones. And this is a sort of example of how we got these sorts of graphs to begin with. And we're sort of planning paths around this graph. So as we can see, so we have a bar chart here, and we have the performance or the probability of completion of each of the methods we found. So the thing to notice here is this green genetic algorithm, the blue box, hopefully you can see it, gives you basically 99% probability that 99% probability of mission completion. And similarly with some other reliability aware methods, we have 90% completion essentially. This is in comparison to, you can probably see the difference hopefully, sort of reliability unaware methods. So it's your standard multi-agent coverage, split the environment in two, where sort of just with standard multi-agent coverage, we only get 60% completion. And with maybe a little bit of a tweak, we get up to 80%. But this is still a far cry from 99%. And we can see this in all of the other cases as well, where we have the reliability aware methods up at 95, 96% completion probability versus sort of standard coverage, which just gives us 27%. So there is a real sort of bonus to thinking about reliability and planning with reliability this way. So just to give some more examples of actual paths, hopefully you'll be able to see this in the PowerPoints that we'll give out. Essentially, a couple of things to point out is with our method, we essentially plan overlaps into our routes. So at the top, I don't know whether you can see it, we have the 3 agents paths all overlaid on top of the BRL. And you can see clearly that they all overlap each other. And what this shows is that overlaps really do sort of, the overlaps provide more reliability. The second thing to notice is up there, I don't know if you can see it, but we notice that when planning with reliability, it doesn't necessarily choose the path which which is done quickest, if that makes sense. So here we see a trade-off between the green arrows, which is the path found by the partition, which finishes early. However, eventually its reliability is lower versus a path which finishes in its best case later, but overall has a greater reliability. Cool. So this conclusion has a bunch of summary bits on it, but hopefully that's been interesting. I'm happy to answer any questions you have sort of offline, but thank you for listening.
Any questions?
Yeah. Has this all been done in simulation and nothing in real world yet?
Yes. So currently we've just been in simulation using simulated values and all that sort of thing. But the current next step, which is what I'm working on right now, is essentially providing some flight infrastructure in the flight arena to be able to fly multiple drones in order to test this in reality. So we have some drones in the flight arena that we're going to run this on essentially to collect some data. Yeah.
So what are you expecting reliability-wise?
So the difficulty here is, in fact, providing this reliability curve. So right now, we just assume sort of this bathtub notion, and we create a sort of artificial bathtub which matches what we think would work. But in reality, what we need to do is we need to collect data from actual drone. We need to collect failure data to be able to model that curve. So I think the accuracy of this method is all down to how well you can model the failure of the drone itself. But of course, this is all stuff that needs to be experimented with and questions to be answered, as with anything when you port it to real life. Any other questions?
Thank you.
Great, thank you very much.
All right, there we go. Hi, so I'm Pernilla Craig. I'm part of the Tactile Sensing Research Group at the BRL, and my work is basically looking at creating a new way of developing sort of tactile sensor control, pretty much, using active inference. So active inference is a theory that was developed in the field of neuroscience as a way of modelling the human brain, specifically looking at how our perception of the world and our knowledge of our actions and their sort of effects on the world play a role in our decision-making process. And up until fairly recently, it has been used pretty much exclusively within the field of neuroscience, looking at how we can model decision-making in sort of patients with things like schizophrenia, where maybe their decision-making process is slightly different to somebody who has sort of a very neurotypical brain. And when we sort of boil this down to its sort of essential processes, we end up with this sort of iterative process, which revolves around sort of prediction, error, minimization. So you would start with a hypothesis about the world. You predict what the future state of the world might look like after you take a specific action. And then after completing that action and observing what actually has happened and what changed, we sort of update our beliefs about that state of the world. And then if there's still some sort of difference that needs to be resolved or something doesn't make sense, you would change your hypothesis and then continue in that process. So one way that I find quite easy to sort of illustrate this is imagining that you just walked into a dark room and you want to find a light switch. You know from your experiences in the world, light switches tend to be on the wall next to the door. So you'll stick your hand up on the wall, and if you don't find it, you'll think, okay, well, it's not here. Maybe it's a little bit higher, maybe it's a little bit lower, and you keep moving around with your hand, getting all of that tactile information until you do find it. Then you switch the light on and you achieve your goal. So that is basically what I'm trying to do, but using a robot. So I'm not going to talk about the maths too much because I know that in presentations that's normally something that is a little bit difficult to get across, especially in a short time frame. But basically, this is what it looks like. So free energy is sort of this measure, I guess, of your free energy in the world, and sort of boils down to your sort of expected difference between what is your actual sort of internal model, so what you believe is going on, and then also that, but with evidence accumulated, so you can change your general underlying beliefs to make them more accurate. And that's all I will say on the maths front. So what I'm actually doing is looking at a perceptual task with a robot. So this here is my robot. I'm using a tactile sensor, which is an optical sort of biomimetic tactile sensor. It was developed at the Bristol Robotics laboratory, and a sort of hemi-cylindrical stimulus with defined position states. So these sort of lines that are coming down represent equally spaced states with X, Y, Z positions sort of in the real world. And also, just to sort of constrain the problem, we define actions that the robot is able to undertake. So in this case, it would be moving sort of one state to the left, one state to the right, or staying exactly where you are. These states probably have about 0.4 millimeter, 0.3 millimeter separation between them, so really they are quite close. But for this specific task, they are also quite well defined. So in the future, it would be easy to sort of generalize them into states, say this is a flat surface, this is what an edge looks like, rather than something that is quite so constrained. But that's what I'll be working on next. So I mentioned before the mathematics. The great thing about this control system is that it's very general. Because it's based solely on the mathematics, that its decision-making process, the only thing that you need to do to change your task, to change your goal, even to change the sort of classifier or modality that you're using is what you input to that system. So I'm using a tactile sensor, but you wouldn't necessarily need to use a tactile sensor. And to change goals and to change tasks, the only thing you need to do is to change these sort of 5 input matrices, which I will go into more detail, but just briefly, we have this A matrix, which represents the confusion between observations and states. So when you touch something, you're not necessarily going to know 100% with 100% certainty exactly what that is. You might need to move around a little bit, get a sense of maybe the texture or something like that. The B matrices, these represent the transitions between states that I mentioned for those different actions. C matrices is sort of a representation of what you might like to achieve. So this is how you would set your goal. The D matrix lets you set sort of any prior information. So if you know what you're doing, if you know where you are when you start, you can preload that in the D matrix, and the B matrix just sets up the different sequences of actions that you can take based on how many actions you're allowed within the test run. So as I said, this is what one of the A matrices looks like for my cylinder. Basically, it's more confused at the center of the stimulus, which makes a lot of sense because where you have less change in gradient, it looks more like a flat surface. And flat surfaces kind of look the same no matter where you are. Whereas if you've got steeper gradients, it's a lot easier to tell the difference between that. These state transitions, again, basically, they would just shift you one state to either side because of the way they've been defined. C matrices. So this is where you can get some sort of interesting stuff going on. Because of the way that you set your sort of desired outcomes in this, you can sort of set up what you want to achieve. So if you want to have like a specific goal state, so if you're trying to find something, if you're trying to find an edge, if you're trying to find a specific object, then obviously that specific object, that state is what you want to be. So that is your goal, and everything else you don't really care about. Whereas if you don't care where you are, you just want to know what you're doing, you don't have a goal in mind, you just would set this to be equal because you don't want to sort of preload that or give it any sort of bias from a human perspective. So for what I'm doing, where I'm investigating the general behavior of this system, having this sort of equal states desirability is really good because it lets you actually investigate what the system wants to do, I guess. Again, D matrices, already explained this. One thing I haven't explained is that it can also be very good for multimodal systems. So if you have a system that's using both touch and vision or proprioception or things like this, you can preload some information from different modalities into that sort of initial state. So if you have a general idea from your vision system of where you might be, and then you want to fine tune that with tactile sensor, it's really good for that. So on to the results. This is sort of in general what they look like. So what I've got here is the behavior or the behavioral trends of my tactile sensor running this sort of localization task. So what's happened here is the sensor has been placed in a random start state, and then with all of the information that it knows about what the sensor looks like and all of that that's been sort of given in these different matrices, it's then decided on the most sort of optimal ways for it to move in order to gather more information and gain enough certainty to decide where it is. So along the x-axis we have sort of tap number, and along the y-axis we have these different states. So in this case there are sort of 61 states at a separation of about 0.4 millimeters, I want to say, for this particular run. And where they're in black, that's where they are sort of correctly localized. Where they're in pink, they're just one state away, and I think there's one in red, which is 2 states away from where it should be. Which in the grand scheme of things is still pretty close. But I think for this particular run, it was maybe asking for about 90% certainty before it would localize, which is why it takes quite a long time to be able to do so. But we do see these sort of consistent behavioral trends where it is moving from more confusing states to less confusing states, which is what we like to see, because that is something that you would do as a person. You would move from somewhere more confusing to somewhere less confusing. And also, another interesting thing that we can have a look at is the belief updating. So this basically refers to the agent's level of belief in its position state. So these sort of white circles refer to sort of correctly localized observations, where it's taken an observation and it's been correct. And the sort of red dot down here is where the observation has been incorrectly classified by the classifier that's used to determine what state it should be in. And what's really interesting is that the agent is able to completely ignore. So this sort of final bottom box here is like after the last sort of action. And it's able to just completely ignore that incorrectly classified data because it understands from previous actions how, like what it would expect to see, and also knowing that it could be confused in these locations. It just decides that, no, that was wrong, rather than having any sort of issues with getting more confused, basically. So I think that's me done, and just got a little summary up here. But if anyone has any questions, please feel free to ask. Any questions? Cool.
So, hello everyone, welcome to my talk. How and when should a robot initiate and terminate a social interaction with a human? So this is all about social human-robot interaction. And so let's start off with the question of when should you act with the robot? Or when should you act, more precisely? So, as an example, I've got a video here that shows a person walking into a business office, and the camera view is basically that of a receptionist. And so if you look at this video, try and imagine that you're doing this task and try and identify the moment that you as a person would initiate an interaction with this person, purely based on body language. And then we have a difference in these two videos. Hopefully they start playing. And then as a comparison on that video, we have this one. So immediately it becomes very obvious that there's a difference in these two people. Whereas the first one walks in, they immediately know where they're going and what their goal is, and they do not require any assistance. Whereas the person in this video currently is more unaware of their surroundings and shows more behaviors indicating that they are uncertain of what they have to do or where they want to go. And this shows in their body language. There's more trunk rotation, there is a loss of velocity, there's not a straight trajectory. And these are signals that we as people are very capable of picking up on and acting on. Now, the motivation here is, can we teach the robot to do the same thing? And as a motivation for the overall project is to improve the overall interaction quality during a human-robot interaction, mostly by ensuring that the start and the end of a social interaction are satisfactory from the human perspective, as that is incredibly important for the overall experience. And we always know this thing that is saying that the greetings and the farewells are seen as like brackets or punctuation marks around conversations. Because the first thing when you meet someone, you get an initial idea of this person that you're interacting with, and when you leave the interaction, that's the thing that sticks with you as well. So it's very important that these two parts in an interaction are done satisfactory, as in human-human interaction, and that also would translate to human-robot interaction. Because there are currently like receptionists or greeting robots, that a lot of the time either rely on the person taking the initiative and doing basically all the initiating or closing of interactions, which is obviously not how human-human interaction works. Or as an example, there was a receptionist robot that would guide people to a certain room when they asked for it, and then when they provided the information, the person would just walk away, and then the robot sat there would go like, "Can I help you with something else?" And then the person would just go, "Oh, so, yeah, no, I don't have anything else." Okay, and then want to go away again, and the robot will once again stuck in this loop, because that's their programming, as, "Can I help you with anything else?" Making this ending of this interaction very unnatural and unsatisfactory. So what we're trying to do is having the robot observe the person, and once this person indicates that they are having received all the information and they are ready to leave the interaction, that the robot can basically go like, "Okay, I am done, I don't need to respond anymore." And what is surprising is that a lot of research has been done on interaction as initiation, in human-human interaction, as well as in human-robot interaction, but surprisingly little on taking lead. And most of the things indicate that people are really good at finding these moments of initiation, but we're not as good at finding the moment of stopping interactions. With some researchers showing that like only 50% of people are actually capable of locating that point. So it's interesting to see how that would translate to robotics. And doing this, we have started taking an online survey to try and help inform our robotic system on what they should look for. So how it was done is similar as the videos I showed before. I've collected an entire database of moments where there should or should not be a interaction initiation, as well as videos where an interaction is ongoing and nearing its end. And these people were basically asked to watch this video. Here you go, guys. And please indicate when, looking at this video, you decide you would start an interaction with this person based on that body language. So there's no audio cues, there's nothing. And for either videos, for either condition in initiation or termination, there were 3 conditions. So one condition was the person in the video does not require any help. That's the video that you saw now. This person just basically walks in, they check their mailbox, and they leave. We assume here that there is very little that the person in the video would pick up on this person needs help, I should initiate the interaction. The second one is a video where the person does not know where they're going. But people being people, they can be very stubborn and they don't want help. So they are sort of not trying to show to the person, which is the point of view camera, that they are in need of help. I call this like the stubborn condition. And so you can see this person basically here, like checking the directory, checking the stairs, should it go up, should it go down, and then leave. And then finally, in the videos, there's the third condition that I will not show now for purposes of timing, though what some will come up later, is one where they will actively seek out or invite an interaction from the camera. So their behaviors of not knowing what to do will be directed more towards the camera. Now, what's important to note when collecting this data set, very little direction was given to the people in these videos. So they were told, you walk inside, you know exactly where you're going. Either you walk inside, you don't know where you're going, but you don't want to show it, or you walk inside, you don't know where you're going, and you kind of want to get this person, this receptionist, to talk to you, and that's it. And this was all done in order to maintain this as natural as possible, the interaction of how people acted, which would then help me if I have multiple different people in these videos, that they either have different types of behavior,
that then eventually we have different types of sets of behaviors that people can look at, that we can train our system on later on. So these are some examples of the initiation videos. Now, these are some examples of the termination videos. So in these, the interaction is ongoing, and in this case, this is the first condition, there is a mutual ending of the interaction. So the person in the video and me behind the camera are talking, and we mutually agree this is the moment of ending. So we expect here that there are very little frames, or like a time of window, where there are actually signals of the interaction has ended. Compared to one where we've all done this, you want to leave, but the person talking to you does not pick up on the signal, but you don't want to be rude, so you're trying to be as polite as possible, moving about and physically trying to show that you're done with the interaction, which is what's going on here. So just a couple seconds ago, the person in the video has like received the hand signal, like you want to leave, and so you start like they started moving their body away. He specifically is reaching for the doorknob. What some people do, some people don't. Some people pull out their phones, some people check their watches, some people look away. So you see that's what's like going on here a little bit, but it's not over exaggerated. It is not very hurried because the direction was try and be polite about it. Whereas the final condition, once again, I don't show a video of it here, but it is very much, you remember you have a bus to catch. You remember you have a previous engagement and you have to leave, which then leads to more hurried, overt behaviors. So that means that in these videos, and hopefully in my data set, I get this like gradation of different types of behavior, as well as different intensity of behaviors. So hopefully when people have done this online survey, I can collate the data and have these nice time frames that I can look at and then feed it into a neural network that tracks body language and like skeleton data that I can then incorporate on a robotic system that they can look at people and do the thing that the people in the videos were basically told to do or asked to do. So when we ran this online survey on Prolific, these are my participant data. About 81 participants took part in it, and they were asked to answer the Big 5 personality questionnaire to see if actual personality traits have a correlation to the types of behavior they're looking out for, or their willingness to actually initiate or terminate an interaction. And so each participant rated 6 videos, 1 for each condition, so the 3 in initiation, 3 in termination, that is a generic like scale of where the people actually come from. But it's maybe not as interesting as the following results, which have been video ratings. So the results vary greatly between my videos. With some videos, as you can see here in the graph, it's very obvious there's a specific moment in this video where people agree almost unanimously, like this is the moment. So if we look at this video, it's around between 3 seconds. So let's see if you can spot what everyone else spotted apparently. So person walks in, and then there's like, if I go back, there is this slight moment of eye contact and a nod of recognition. And everyone apparently watching this video went like, this is the moment. And that's great. I was hoping I'd find something like this. Unfortunately, that is not the case for every video, as evidenced by this graph. So this specific video was rated 5 times, and I had 5 different moments where people said they would initiate the interaction. So if we look at it here, what's going on here? So, okay, one person said immediately on opening of the door, this is when I initiated. Another person was like, oh, this person is like sort of milling about. This is when I initiated. Another person, eye contact. This is when I would initiate. And then at the moment of like standing still, other person says, I would initiate. So going through the data further on, I sort of have to take out these moments, see if they correlate with other behaviors that people have seen, if each person rating the videos would actually look at, is this person specifically looking at eye contact, is one of the things, and some other like measurements that I have to figure out what is happening. Some videos kind of lie in between, which is evidenced in this graph, where initially it didn't really show that there's like one point of where people would initiate, or in this case terminate, but if we put it in a graph, we can see there's actually a band of time. And looking at this video, we can actually see that it is the same behavior lasting a couple of seconds, and then the people rating the video just have decided on slightly various point scales. But we can make the argument that this is the same behavior. So this is the time frame we should look at. These are the skeleton data that we should look at. So 9 to 12 seconds. So it's the wave, and the turn away is the departure where everyone's decided this is when the interaction should end. So this type of graph is the one that is most common in my data. So there has to be some more analysis that has to be done, some more post-processing in order to actually be able to feed this type of data into a neural net to be able to train it on. So similar in this one, you can see this nice band here, where apparently most people agree this is when I should terminate the interaction. And then there's like some slight variation where we still have to look what is exactly going on in order to see what type of behaviors we should feed into our neural net. How am I doing on time? Yeah, okay, so just see if we can we can spot the moments here when someone would end the interaction. So interaction's ongoing. This again is a polite situation. About now is when I waved, and you can immediately see the person like step away, cross their arms, sort of close themselves off to indicate that the interaction's ending. And then there's a lot of milling about. And this specifically has one movement where it would trigger most people. So let's see. That one. So I don't know if you all here in the room agree that that is a indication of I gotta go. But apparently people rating the videos were very sensitive to this specific behavior. And unfortunately, this is just a mess. And unfortunately, it's myself. So in this one, I believe this is the hurried one, where I remember I have to be somewhere else and I want to leave. So I'm speaking and I was like, okay, just please let me go. This could be because I'm personally like very animated in how I speak and how I act, which might lead to a confusion or an abundance of signals that people can choose from. But yeah, this is the things I have to deal with now after this survey. So for future work, it means that there's more in-depth analysis required due to the very nature of the replies that I've gotten. It means that I have to look at these clusters that I showed before. It means that I have to do data labeling on what are actually behaviors that last multiple seconds. And see if actually differences in personality are affected. Initial viewings have seen that anecdotally, there's one participant who basically in the personality questionnaire does not care for other people, hardly shows any empathy traits, And we were able to see this in the videos, in their ratings, where it was, nope, I wouldn't initiate. Nope, I wouldn't initiate. I'd only basically initiate when the person in the video walks up and goes, please help me. So that might lead to personality being actually a factor here. But I hope that it would provide us with enough training data once this data set is completely properly labeled and checked. So for my project outline, it's I have to know when to act. Then, if I know these moments, I know I should figure out how the robot should act, which probably is another survey. Then I should train a neural net to recognize and classify the social cues. I have to implement path planning and behaviors on a robot platform, because obviously it's going to be an embedded and embodied system that will actually observe people and decide this person needs help, this person does not need help, I should approach this person. So the path planning and behavior is all an element of my project as well. So hopefully the finished system should look something like this, is where we start off with a camera, currently a Azure Connect, which reports RGB streams, depth data and infrared data. It streams that video to a PC running the vision system. The vision system would then detect the person and classify the body language. It should send that classification to the robot, which has a behavior list, and it should select the behavior based on the classification. And then the required behavior is sent to the robotic platform, in this case a Pepper robot. It would perform the behavior and change the camera position in the current system where the camera is mounted on the robot. And then loop keeps going until the interaction's ended and they should look for a new person to interact with. So in all, that's my talk. Thank you for listening. And if there's any questions, I'd be happy to answer them.
So we have a couple of questions from the chat, right? If you train your system based on these semi-empty clips, do you think this will work for real-life interactions, where the social cues might be more subtle? And so is there any ethical way you could get a data set of real-world interactions?
Yeah, this is obviously a point of contention probably, because the data set that has been recorded is not people acting in a natural situation. So the argument can be made that some of the behaviors are not as natural as possible, or are not indicative of how it would happen in a more noisy environment. But we believe that it is still a like a stepping stone for a data set that we can actually use to track social cues, and hopefully that would translate to real world situations, maybe more noisy situations. But that is currently still something that we have to look into.
Anybody else? Thank you.
Thank you very much.
Be basically, or unfortunate bugs. And so what do we mean by verification? Verification is the process of evaluating whether or not a system complies with given specification. In other words, it's to prove that certain properties always are guaranteed by a system, or let's say specific errors never happen. Verification can be done using test-based verification methods, or by formal verification methods. In my PhD, I'm focused on inspecting the application of formal verification methods to planning based systems. So to get a better idea of formal verification, we start from a given specification or a requirement for a system, which the designers use to generate an implementation. And this implementation, to verify this implementation, we extract an abstract model that describes this implementation. And also we extract from the given specification a list of properties that we would love for the a system to have. And then we feed this abstract model and the properties to formal verification methods such as model checking to see which properties are satisfied and which properties are not satisfied by this implementation. This then unsatisfied properties or false properties will be given back to the and a counter example, if we are using a model checker, that will be given back to the designers to fix their implementation to match the given specification. The advantage of formal verification is that it offers high level of assurance about the correctness of systems, unlike the testing, which only shows us the presence of bugs, as Dijkstra says, but never testing can show, but testing never can show the absence of bugs, which can be done by using formal methods in a certain abstract level. And formal verification is also exhaustive and rigorous, so it covers the entire it should cover the entire search space. Now I would like to give an idea about the general idea about the planning-based autonomous systems. In the core of these systems, we have planners. Planners are intelligent search algorithms that search for a sequence of actions to transfer a system from its initial state to a goal state. And the inputs for a planner are a planning domain model. A planning model is a description of the environment and available actions for the planner. And also a planner would take a planning problem as an input, and the planning problem describes the initial state of the agent and the initial state of the environment as well, and also it will describe the goal states or the goal conditions need to be met. And then the planner would search for the sequence of action, which is the plan returned by the planner for this specific planning problem. And then the plan is transmitted to an executor. The executor will apply the actions of this plan on the plant, and the plant can be a robotic arm or a rover or any agent in the environment. And then we have the monitor, which monitors the agent in the environment and estimate the current state of the agent and the environment and feed this back to the planner, which then depends on the current state, and the expected state would decide whether a new plan is required or everything is going as per the plan, basically. And in my PhD, I'm focused on applying the formal verification methods to inspecting the correctness of planning domain models. Our investigation showed that there is a shortcoming in the application of state-of-the-art planning domain models verification methods using model checkers. So basically, yeah, our research showed that there is a shortcoming in the applying model checkers to verifying planning domain models, and that's because model checkers takes the available actions and try all different possible sequence of these actions to see if the planning domain model at hand can be used to generate a sequence of action to reach an erroneous state, whereas a planner would only consider any sequence of actions if it ends by a goal state, if it enables the agent to reach a goal state. For example, in the microwave oven, we have these 4 states. In the initial state, the door of the oven is closed, the oven is not in starting position, is not in start state, and there's no error, and there's no heating. You could either close the door, then start the oven, and then you reach a state where the heat's on, or you could just start the oven before closing the door, and that would reach to an error state. And let's say the property, given safety property is G, that's from the LTL logic, that stands for, means globally, we should not be an erroneous state. And if you give this model to a model checker, the model checker would return a counterexample starting the oven, because this sequence of action starting the oven would reach an error state, and that for model checkers is a counterexample. On the other hand, when this model is given to a planner, the planner would never, a sound planner would never return start oven as a plan, because it does not really terminate in a goal state. So this branch would be terminated or pruned basically by any sound planner. So the solution for this problem to basically we need to modify planning domain model checkers to not return false positives, a counterexample that are really not reachable by planners. So for that we have introduced our concept of a goal constrained planning domain model verification, whereby we reject any counterexample that simply has no potential of reaching a goal state. And we have shown how this can be implemented for using the spin model checker and also using MIPS XXL planner. And this work was presented in 2020 in STERS conference. And the second piece of work is the investigating the functional equivalency between planning domain models. So we found that interesting to see how can we prove that two different planning domain models are actually functionally equivalent. So let's say we have two domains, D1 and D2. As you see from the block word, as you see in the domain 2, we have the unstack put down action, which does not appear on the domain D1, and also D1 has unstack, which does not appear in D2. We still argue that these two domains are functionally equivalent, that can be used in place of each other. To achieve the unstack put down in D2 using the actions in D1, simply you have to do unstack followed by put down. And similarly, to achieve the unstack functionality in D2, you have to do the unstack put down followed by a pickup. This is really interesting piece of work because it has so many applications, such as evaluating the quality of automated planning model learning algorithms, validating planning domain models optimization methods do not alter the functionality of the original domains, or simply to check if two planning domain models that are allegedly represent the same domain are actually equivalent. This is an example from the literature where a handcrafted domain is fed to a planning model learning algorithm, and then a sequence of actions that plans generated from this handcrafted domain are fed to a planning model learning algorithm, which learned this kind of states, which what you can see both are they supposed to express the same domain, but because the learning algorithm might learn different names of state, that can be challenging. To solve this problem, we have defined the concept of reach set of planning domain model, basically this all state that can be reached from any initial state of a domain. Then we introduced the theorem to enable the reach set comparison by inspecting the structure of the domain's operators rather than inspecting and iterating over all state of a reach element of a reach set, which is there's infinitely many states. And for that we have developed a tool that can prove the functional equivalency, and our tool uses a combination of planning and SMT solving techniques. Thank you very much for your attention.